vary three things: the depth, the fluid density, and the gravitational field strength. Let's first off by pull this pressure gauge out and notice that it's measuring the pressure from the atmosphere. We're interested in measuring just what the fluid pressure is. We know that the atmosphere is going to be pressing down on the fluid with about 100,000 pascals. Here they've got about 130 kilopascals. But I want to focus on just the factors that affect the pressure in the fluid. We know the atmosphere does for sure, but what are the other factors? So we're going to get rid of the atmosphere. We're going to click this little button over here, and we're going to turn the atmosphere off. What we're going to do is we're going to vary three things. We're going to first vary the depth. We're going to start by putting it at a depth of 1 meter, and notice it's 10 kilopascals. If I double that depth, I'm at 20 kilopascals. If I triple that depth, it doesn't let me get all the way down there, but you notice it's going to be triple as well. So that's a linear relationship. If I double the depth, I double the pressure. The next thing I want to vary is the fluid density. You notice I can change the fluid density all the way down to gasoline, which is 700. And you notice that I have a value of 7. If I double that value of density to 1400, you'll notice that my pressure doubles. That's also a direct linear relationship. The last thing I want to do is put the density back to 1000 for water, is vary the gravitational field strength from the lowest value they let me do, which let's actually go to about 5. I'll write that in real quick. And it tells me my pressure is 5 kilopascals, so my gravitational field strength is 5. If I double that to 10, then my pressure is doubled to 10. And if I triple my gravitational field strength to 15, you'll notice my pressure triples. So those three factors, depth, fluid density, and gravitational field strength, are all directly related to the pressure exerted by the fluid. I also, of course, know that if I turn the atmosphere back on, that's also affecting the pressure. So let's go back to my presentation and look at the equation for the factors that affect the pressure exerted by fluid. That's my equation up there on the top left. Pressure is equal to P naught plus rho GH. P is my absolute pressure. That's my total pressure. In that previous example, it would be the air pressure, the atmospheric pressure, plus the liquid, the water, whatever density I changed it to. That's that P naught atmospheric pressure. Remember, we're going to say that is 100,000 pascals, and that's on your constant sheet. Rho is the fluid density in kilograms per cubic meter. Gravitational field strength is in newtons per kilogram. For MCQ problems, we just always assume that we're on Earth, so we're going to use about 10 newtons per kilogram. The H is the depth under whatever fluid you're talking about. And then finally, rho GH is our gauge pressure in pascals. In the previous video, we used a tire pressure gauge that measured the gauge pressure, just the pressure inside of the tire that's only due to the air inside the tire. It's actually more pressure in there. The absolute pressure inside of a tire is more than what the gauge pressure tells you, because it's measuring the pressure that's more in the tire than it is outside the tire. Atmospheric pressure is about 14 psi, so the measurements that you're reading for the tire pressure gauge are actually slightly less than the absolute pressure inside your tire. So we're going to do two quick practice problems now that we know the equation for pressure. Our first practice problem is going to be investigating the fluid inside of a closed pipe. The picture you see is a closed pipe, and the valve is going to close off the end of the pipe, but the pipe is still going to be filled with water, which we know has a density of 1,000 kilograms per cubic meter. They're interested in calculating the absolute pressure at point A. Remember, absolute pressure is the pressure that includes the effect of the atmosphere. You'll notice that the vertical position at point A, how deep underwater it is a total of 6 meters. The width of the pipe and the horizontal position is not important for us to know. All we need to know is the depth, which is 6 total meters. Our equation for pressure is pressure, P, is equal to P naught, which is atmospheric pressure, plus rho GH, which is density of the liquid, G, gravitational field strength, and H is depth. So our absolute pressure is the atmospheric pressure, which is 100,000 pascals, plus the density, which is 1,000, Gravitational field strength, we're just going to use 10 newtons per kilogram. And then we know that the depth is 6 meters total. When I do all that calculation, I get a total absolute pressure of 160,000 pascals. So that's our first example problem. Let's look at our second example problem next. How far underwater must a diver go in order to experience a gauge pressure equal to the atmospheric pressure? And we're going to use the density of water as 1,000 kilograms per cubic meter. So they're interested in what is the gauge pressure, that's rho GH, when that's equal to atmospheric pressure, which we usually say is P naught. So if that's 100,000 pascals, and my density is 1,000 kilograms per cubic meter, and my gravitational field strength is 10 newtons per kilogram, what depth do I need to go to? If I get rid of some of these zeros, I notice that my depth is 10 meters. That's very far underwater, probably farther than most folks have ever. I've not been 10 meters underwater before. So in order to get the same pressure from water just alone that we're getting from the air now, in order to double the pressure we're feeling, basically, we'd have to go 10 meters underwater. So what should we take away from this video?